Hello everyone, welcome back to Scientific Panchayat. So let me start with a very basic question. Have you ever looked at the night sky and thought, how did this universe begin? Where galaxies come from? And how do we end up here sitting on this tiny blue planet and asking these questions? So today's episode is exactly about that. But don't worry, we are not going to make it like a physics lecture. We'll try our best to make it less technical so our viewers can understand better. Today's guest working on cosmology and he studies about the very early universe, like it's the time before formation of stars, galaxies, and even before we existed. So we'll talk about his research journey, his career, and what he thinks and other things about his PhD life. And we'll also talk about other things in academia, or like how politics affect the research and what are the funding situation right now in Europe or specifically in Spain. So the people who's thinking to join their PhD or the postdoctoral position in Europe, they can have the better idea. So these kind of things we are going to cover in this podcast. So first of all, I'll welcome you here,
Thank you.
and I'm really happy to have you here. And we'll try, like our audience can get the maximum knowledge out of this conversation. First, like before going to start, I just wondering how you are feeling today.
We feel fine.
Are you nervous or excited?
Yeah, I'm always excited to talk about my career and also about science in general. Is one of the passions of my life. I wouldn't be here if this wouldn't be a passion of mine. So it's always exciting to talk about this. Yes.
Okay, so we'll divide this conversation mainly in 4 or 5 sections.
hmm
So first we'll start with your journey, like how you come up with the idea, like you really want to be a researcher. How do you think about it, and what are the things that get you here at this
All right.
position? And then we'll move on to your research work, which followed by like the struggles during the hard time in research or
hmm
during your PhD journey.
Yes.
Then we'll discuss like some other things related with the politics, research environments,
hmm
and what are the things that can be improved in academia. So these
Okay.
four section I have in my mind, but we'll see as we talk.
Yeah. Perfect.
So like I would like you to introduce yourself, what kind of a person you are, within the academia or outside the academia.
Both aspects.
Yeah, both aspects.
Okay, so I'm Guillermo Martínez Somonte. I'm a final year PhD student in Santander, which is a medium-sized city in Spain, in the north of Spain. Well, and yeah, I think one of the good aspects of my life is that I really passionate about big and also small things in my life.
Oh, great to know. Like my first question is, were you interested in science from your school time, or it came later into your life?
Yeah, it was quite early in my life. I
Okay,
mean, exactly when I was a kid, a little bit not very, but just a little bit obsessed with numbers. I
okay.
kind of like numbers. I was good with
Mathematics
with
then?
mathematics, with just like doing sums and multiplications and all of this.
Okay.
The-
Then
Mhm.
why do you decide like physics or mathematics?
Yeah, this is like when I was a kid, but when I grew up a little, more in the high school, I tend to realize that I was interested more in why, the question why of
Yeah,
things, more than how or things are done, or for example, I don't know exactly how a engine of a car works. I
yeah.
mean, I mean, I don't know the parts and the ingredients and the different components. I just more or less know how it works, and that's okay for me. And I realized that my interest is more like fundamental of
Okay,
stuff.
fundamental aspects.
Yes,
So
which
you,
has a good point behind, but also has a bad part behind. Because also knowing the components and the
yeah,
how is also important.
yeah,
So
yeah.
yeah, I kind of felt like I was interested in why things happen. No,
The audience would also like to know, was there any moment in your early time, like when you were a kid, when you just looked up the night sky and think about the stars? Like there might be like constellations, and specifically if you are observing night sky in
Mhm.
winter times, then you will be seeing the Orion and other constellations. Like, so have you done this observation when you were a kid?
So I'm sorry to say, but really, no, it was just the images that I have in my mind and that really amazed me as a child were just illustrations in books and also in movies or in the TV. I
Okay.
was, in fact, I am not still nowadays really very fan of observing the sky. Of course, I like it a little bit, but I am not passionate about really. It's funny because I am passionate about my work,
Yeah,
but not about observing the actual sky.
yeah. Okay, so from the conversation so far, it's quite clear you always wanted to be a researcher.
Well, I have many doubts, but of course it is. Yeah, I guess that's the job to find out why. No.
Yeah, I really like that inspiration, like always running after why,
Mhm.
because these are the simple question that leads us to some massive discovery or
Also, more
idea.
questions.
Yeah,
That sometimes you start with one question and end up with even more questions, but at least, well, in the middle between you get to know a little bit. No, physics was for me in the high school quite boring because
okay.
this inclined. I mean, to just track the forces of an object, that this inclined movement,
Yeah.
quite boring. But then it was like a contrast with knowing the universe and this fundamental.
So the next thing I would like to know is based on Indian student mindset.
Mhm.
So like many Indian students think researchers are naturally brilliant from their childhood. So was your journey like that? Or did you also face some confusion?
Well, yes, I think I consider myself intelligent in comparison to the other kids in general. I think I was really a really good student at school, but really because I had interest in knowing stuff. And but I brilliant. I wouldn't say brilliant. Just maybe slightly above average.
Okay.
But I think that also there is an aspect that for sure we will talk later. That is not as important to be brilliant or very intelligent as comparison to be disciplined at your work, to really have interest in study, and
Yeah.
gather more knowledge.
So that means you don't need to be a brilliant. Main thing that is the essential thing in the research is your passion
Mhm.
and your interest towards the research, and then the how good you are at based on intelligence level that we define in a biased way. I
Mhm.
would say it doesn't much affect of your research work or
No, not at all. I would say I would say that a total average person could be a really great researcher
yeah,
for
but
sure.
it
Never
he
mind.
should follow like the patience and their interest and how passionate they are towards the research. These are the key things to be a good researcher. Or do you think anything else apart from that?
Well, I would say that okay, the research part has a good aspect of really studying the universe and obtaining great results and being able to test of the theories and all of this, but also has the other aspect of really it's another job. Like any other job, you have to be a routine. You have to do many stuff that is a little bit boring, little bit flat. Just I don't know to make figures for an article. You struggle with so many problems that like any other job. And I think that passion in there is important to really get through these moments and to being able to focus on the good part. So I will say that yes, I think that's the better motivation for a researcher is passion.
So, who influenced you the most? As you explained, like you were watching the movies, you
Mhm,
were reading the books during your school time.
mhm.
So, who influenced you the most to choose this research field? It's either the books or movies, or maybe a particular teacher from your school time?
Well, in the high school, I will give you two answers. In the high school, I had one teacher. One teacher, it's called Álvaro Polidura, was called as teacher here in Spain. He was a great physics teacher, and I remember exactly. I did an exam. I think it was related to things of gravity and the time. Look,
Okay.
this
Yeah, like the
by chance.
Newtonian gravity is
Yeah,
that
but
time.
but it was funny because I didn't knew one aspect of one problem, and I
Mm.
had with zero idea of the problem. I had like to from zero from scratch. I started like to do like some trigonometry and some triangle or whatever, and I think that I think I don't know where I end up in this problem, but the teacher really evaluated that.
Okay.
Like okay, you did okay, maybe you didn't get the right answer, but your derivation that you did here is interesting, and
Okay.
I felt like okay, wow, maybe I don't need to memorize many stuff,
Yeah.
and well, maybe my knowledge and my way to explain things is also interesting, and I think that's motivated me to pursuing this research in life. And the other aspect is exact movie. Well, I was studying physics already, but it was a movie Interstellar, which is
Okay. I think it's everyone's favorite.
yes, it's a topic. Sorry, but I really watched the movie for the first time, and I was like finishing my undergrad studies, and I realized like wow, maybe when I was a kid, I like this space stuff, planets, and all of this, and I feel like I reconnected with that
Ah,
watching that movie, and I think well, I can focus on this field.
okay. So I think this is important because many students only see the final title after you've done your PhD. Then you just get the doctor in front
Hmm.
of your name. So the many students think or only see that title, PhD researcher or scientist, but they don't see the confusion behind this title, like how many failures you have gone through. That's what I think. Like the mostly student think it in a don't think in that aspect. They think
Yes,
like the researcher must be brilliant since their childhood.
I get it. Yes, no, not at all, not at all, and there are many paths to arrive to be a PhD or just a grad student or whatever, and really sometimes it's not the best indicative on the person behind.
Yeah,
I said the good part that really an average person can, I think, get a PhD and really be a good researcher. But also, I think to be brilliant and also very intelligent people, okay, maybe they have a PhD or whatever, but maybe they are not a good researcher. Maybe to work with them is not easy at all. So I will say it's more complex, and also, as you say, the final goal is not maybe it's not the best indicative for the
yeah.
person who is behind
So
this.
it's misconception
Yeah.
among students who really think they have to be really good.
Yes. Yeah, it's sure that, for example, I think to have a PhD, well, at least it indicates that that person has passed through some epochs in their life, that for sure this person must have some struggles, but okay, I don't know. In general, you can get such a big variety of people that really the title the is not the best indicator.
So if we conclude this whole section, so the key thing I can grab out of this
Mhm.
is that the intelligence is not the solo metric to measure your willingness to do science or research.
For sure, it is
Yeah.
not.
So don't get be confused if you are not brilliant as others. You just only need dedication, your passion, and your interest to follow along your research.
I really think so. I really think so.
Now we move to the next section where we'll talk about your research,
Yes.
what you are working on,
Hmm.
but in very
Divulgative way.
yeah. So we'll try to skip the technical terms,
Hmm.
and if we use some technical terms, then we try to define them so that
Yeah.
our broad audience can relate. Like, let's say if you use the power spectrum,
Yes.
in
Well. Okay.
then we'll try to understand the people what does power spectrum mean.
Yeah. Perfect.
So this way we'll try like it's more like less physics there.
Yes, I think it's important to do this stuff because at the end, 99% of people they don't know about this, and
Yeah.
sometimes they just technical words, even for photon, for light.
Yeah.
And people get, what is photon? Well, come on, use light. I
Yeah.
mean, most times light does the work.
Yeah. Otherwise, become a physics heavy lectures.
Yeah, and yeah, we are all day working with this,
Yeah.
so it's important to be able to
Yeah.
change this.
So that is
So,
that.
well, my research really is quite connects the theoretical aspects of our knowledge of the universe with what we observe. It's more what I study is the large scale of the universe, more big than even the galaxies and the small clusters of galaxies that we can see. What I study is just the most large structures in the universe. These structures we cannot see directly with telescopes and whatever, and we really need to do this mapping of a structure of galaxies in the universe. So I work in knowing the properties of this distribution of matter to see how separate are these different galaxies and clusters of galaxies, if some structure is formed at certain distances or not. And I study these space properties of how matter is distributed across the whole universe. And the
So
point in studying this distribution is to link it with a fundamental theory of the universe that cosmology provides, which is called cosmic inflation.
okay, that's really good way to define the cosmic inflation.
Yeah.
Otherwise, people might wonder why we do need this cosmic inflation.
Mhm.
Because what I remember from my cosmology course from University of Bonn, they started with why do we really need the cosmic inflation,
Mhm.
and they come up with lots of technical words like
Yeah.
the we introduced cosmic inflation in order to avoid the magnetic monopole
Yeah.
and other things as well. I don't even remember now, but the few things that I remember, the very first thing they talk about the causality effect,
Mhm.
like the pitches which are causally disconnected and all,
Yes.
and other thing they talk about the monopoles.
The monopoles and the flatness, no, probably on the universe.
Yeah. So like we use few technical words here like
Mhm.
the clusters and the
Yes.
mapping of galaxy. So could you
Mhm.
explain what you meant by cluster and when you say mapping of galaxy catalogs?
Yeah, well, the clusters are fundamental properties of galaxies that they are not isolated in general in the universe. If you start to study some galaxies and you observe them and their movement, you can see that some of them are aggrouped in some group of galaxies which are called clusters of galaxies that are bound more or less with gravity.
So
Because in general, other galaxies and other clusters are not bound by gravity, but if some of them are quite close, they become bounded and they become this cluster of galaxies. And regarding the maps, it's just different techniques to study the position of these different
So when you
galaxies.
say
Yeah.
map, so you are capturing picture of that particular sky position there
Hmm.
across different optical windows, or
Hmm.
like maybe like infrared window, or like the optical regime or radio regime.
Yeah, in my research, I mostly work in the optical regime, in the light that we can see with our eyes. But this mapping of a structure can be done across radio frequencies with X-rays, with different frequencies. And what we do is really to have all the sphere of the sky and really to map a structure from the most close to us, galaxies to us, to the farthest ones. And we do this like a 3D map of how the structure of the universe is represented. It's just have locate in a grid, a 3D
Okay.
grid, the different galaxies that are found in the universe.
Okay, so I get few follow-up questions here.
Mhm.
So I think the audience who will be watching our podcast, they belong to like the primary school, higher school, some undergrad.
Mhm.
So we'll try to address the most basic questions
Yes.
with very simplest way. Question: when you say what do you mean by the early universe, because we have used it quite a lot of time, early universe, so our audience might want to know what does it really mean.
Yes, in general, in cosmology, there are a distinction between early and late universe. In the late universe, we mostly track how structure is. It's already the seeds of a structure of galaxies are already there, and it's just like the it mostly follows the how gravity acts, how the different galaxies exactly their shape or form, how they are distributed, how they expand, and this is what we call late universe.
Okay.
But the early universe is more related to the origin of things, how the particles were originated, how the universe started to expand, how these seeds of a structure of galaxies were formed, and there is this kind of distinction. Early means more or less origin of stuff.
Okay, so as you said, today whatever we see, whether it stars, galaxies, or some large scale structures,
Mhm,
as you explained, like the clusters.
mhm,
So from this conversation, I found the seeds are the main reasons.
mhm.
That's why we are seeing all these structures today. So
Yes.
what are those seeds?
Well, I will put an example again linking with the why,
Yeah,
because when we get explained what the solar system is, for example, we get that we got explained that the planets rotate,
yeah,
and okay, the certain velocity and
yeah.
whatever. But once again, linking this with why do they rotate? And it's related to the formation of the solar system.
Yeah.
And at the end, the solar system, it's a little part of our galaxy that was formed within the galaxy. But these seeds, I mean, why did the solar system form? Why did the galaxy form in this way? Why did the galaxy is in between a galaxy cluster that I talked about before? I mean, you have to relate these objects that these objects were formed at a certain point in the late universe. But really, we need some seeds, some perturbations
Okay.
from the standard universe. We have a model for the universe, so for the model of the universe, how it evolves, but we need really some deviations from this background. And these small deviations are the one that in some region there is a little bit of more of energy or more whatever, and this ends up evolving, creating a galaxy cluster that will be formed there.
So the seeds, like basically you are putting seed under the ground, and after some time or the
Yes.
years, you've seen a grown up tree. So you are just trying to locate how
Yeah.
this seeds. Yeah,
Perfect.
yeah.
And in the early universe approach, we try to investigate and know more about the seeds.
Okay, so we are just stretching backward in time.
That's it.
Yeah, we are not literally going back in time, but like,
Hmm.
yeah, because
Yes.
people usually get confused, like when say the cosmologist observe the universe in backward in time. So
Hmm.
can you explain that in very simple way by avoiding the conflict of like how someone can go back in time and study the universe?
Yes. The key factor here is that anything can travel faster than light.
Yeah.
So light has a speed that was measured so many centuries back, and it's a fundamental law of physics that anything in the universe can travel faster than light. So really, when we observe the universe, we are observing things that are very far away, and we are studying them by seeing the light of these
Okay.
objects. So if these objects are so far away, the light will take certain amount of time, a big amount of time to reach to us. So
Yeah.
that's the point that when I say that, when it's said that we see things as they were in the past, is because the light has been traveled for these so many years to reach us. And really we are seeing the light emitted at that time.
Yeah.
So a good example is to say how would in the closest galaxy in Andromeda,
Yeah. Andromeda
how they will see the light that it was emitted
from Milky Way.
from the Milky Way and
Yeah.
from even the planet Earth,
Hmm.
and they will see dinosaurs.
Yeah.
They will study us like dinosaurs if there is life
Yeah.
there, because our light is still just living the solar system,
So that,
and the dinosaur light was emitted so many million years ago. Is the light that is reaching Andromeda now?
so it's bring me to a like very philosophical way
Hmm.
to understand this. So
Yes.
we are kind of immortal in philosophical sense,
Yes.
like like the light interact, like still we are emitting some photons or light, so
Hmm.
they keep traveling. So if someone would able to observe those lights, then they would able to see us. So
That's
in
it.
that way, like it's very philosophical way.
Yeah, yeah. It's like something which is will be traveling in the universe forever. No, it's
Yeah.
yeah.
So but don't you think that it's based on the reference frame, like because we are the ones who is observing the light, and that's why we are seeing light is taking time. But if we go into the Einstein theory
Mm-hmm.
and we say like the light is the fastest things that travel in the universe,
Mm-hmm.
but if we think about from the perspective of light, then what happens with time? Would it be frozen? Think about how photon perceive us, because we
Is
said like we are observing the light that emitted
mm-hmm.
back in time and it
Yes.
takes time to reach us,
Mm-hmm.
right? But it's the whole calculation based on what we are perceiving here on earth,
Mm-hmm.
right? But let's swap the things.
Mm-hmm.
how
Well,
photon would how light would see us.
how light will see us. Well, I am not very sure about this. Funny things happen in the theory of relativity when you go into a frame with the speed of light. Well, if first of all, with matter, anything with matter cannot reach the speed of light
Yeah.
because it takes an infinite amount of energy to
Yeah.
take it there. So really, I'm not sure about question, but I think the fundamental aspect is that time, the speed of light, and time are related, and really we observe things in our time frame because we are moving at very slow velocities in comparison to the speed of light.
Yeah.
But
So
really, if we were able to travel at velocities close to the speed of light, will be in a what is called a relativistic frame. Yeah, for sure, we will observe a lot of distorted stuff, the light signals. There is a funny story that I always like to tell and remember that if you go fast enough, a red light of a traffic light
yeah.
will be green. So stuff like this, I guess, to be on sitting on a particle light will be sort of kind of funny things.
Yeah. So you said you are observing the old part of the universe, right?
Hmm.
So how do you observe them? Like as you said, you map the maps, you use the optical filters or whatever you just said.
Hmm.
So how it actually happens?
Well, there is other tools, no, studying the first light emitted in the universe that we can measure it. But really, what we see is just in my research is just how these structures, big galaxy clusters and even superclusters, which are just the bigger clusters, we can study different parameters with different statistics of these objects, different, for example, as we have in basic statistics, the mean or the standard deviation. We can study other properties to see if some of these properties of how are they distributed correspond to a fundamental part of the universe. So really, we just study the position. We just use these maps of galaxies, these galaxy surveys.
Okay, so with using these surveys, we are looking for the clues, what left behind,
Mhm.
right? So it's
Yes.
kind of a detective work.
Yes.
So I would
Yes.
say the cosmologists
Mhm.
are not only the researchers, they are kind of detectives.
Yes. A little bit. Yes.
Yeah, because you don't see event directly. You rely on the
Mhm.
clues that left behind
That's it.
uh, after the event that happened.
Yeah, a good example is a galaxy clustering in which, because they, as I said, they are bounded with gravity and they have some velocities caused by this bounding. As we are moving with respect to the sun, the different galaxies move between each other. But that's an effect of gravity. That's an
Yeah.
effect of the late time universe. If you want to trace back how this was formed, you have like to take subtract these velocities. And this is like a good example with the structure of the galaxies that I work with. I have also to subtract effects that not come from the early universe, which is also called primordial. But maybe I
It's
don't
a
want to
very
enter into
fancy
this.
word
It's a very
for.
fancy. It's just the primordial is just related with the origin of the universe.
Yeah, so it's we can say it's a very ancient part of the universe
That's it.
that we are referring primordial.
That's it. Primordial relates to the one that originated in the origin of the universe.
Yeah, it's like a treasure you find from your ancient time and you just say it's really
That's it.
aesthetic.
That's it. Yeah.
Okay, so we talked about very much galaxy surveys.
Hmm.
So what are those in simple language?
What are those?
Yeah.
Yes, and they are just a big amount of information in which you have the light emitted by a galaxy, and you can get the information about this light.
So
With this light, you can know how big is the galaxy, how far away it is, how it is moving, and we do that with the most objects as possible in the universe. That's a
okay,
galaxy survey.
okay. So are there any observatories like that specifically doing these kind of things here on the Earth and as well as in space?
Yeah, and the most precise ones are usually now in space, but we had in the past and nowadays many here on Earth. For example, I think the most popular ones are called DESI and Euclid, and also yeah. Well, I think these two are the most nowadays the most popular one. And yeah, the Euclid, for example, is a space telescope, which is trying to collect light from space, from different regions of the space. I will It will map most of the sphere of the sky, and we will get this information about it will reach light which is very far away, and also light which is quite
Very
close,
close.
and it will do this map of in 3D
Okay.
to know all the structures of the universe.
Okay.
And yeah, there are many other experiments on Earth planned for the future, and some of them are better in some range of light. Some others are better in going deeper into this
Space.
3D map.
Okay.
Yes, the different ones have pros and cons.
So it's basically making a huge map of the universe by
That's it.
different light windows.
That's it.
That's it.
Mhm.
And then later you will combine everything together to find the clues
That's
there
it.
to answer your questions.
Yes, this is a huge amount of data. You can
Yeah.
have more than petabytes of data, which is a huge amount. It's just only position, velocities, and all of this. It's not like a video, no. It's not.
Yeah.
It's just terabytes and petabytes of
Yeah.
information about
Yeah.
only this. So you can imagine that
That's
just work with
huge
this
data.
data is yeah, it's another field of
So
of
do
science.
you remember the Spider-Man movie dialogue? Like
Mhm.
it says, with the power, huge responsibilities are coming towards you. So
Yes.
it's the same thing in cosmology or in research. With
Mhm.
huge data, you have the huge responsibility to manage it and decide which data you will be keeping for your research work, and you
Mhm.
also need to decide whether these data points are the true data points or are there any kind of some noise or the artifacts.
For sure.
So it's
Yes,
a tricky job.
just to work with data and know which data is good enough. If there is some problem with the data, it's just a whole branch of science of research, which is a little bit foreign to me, but it's fundamental in our work. If I wouldn't rely on these maps, my work will be zero valuable.
So that means the people who are good at in data things, like the
Mhm.
data analysis
Yes,
and in those kind of stuff, they can also make really good career in research as well
for sure, for sure,
because we
and
have the huge data.
for sure. For example, me that I collaborate in some of these surveys, what they want more is to get some secure stuff on secure schedule and how this processing of data is doing, and because it's fundamental for it's the base for then perform science on this data.
Oh,
So yeah, really is in the for really to have a job position is fundamental in science, in cosmology in particular.
okay. Why do you think the people who is working in cosmology they would require the millions of galaxies rather than the few ones?
Yes, because because the main reason is that because the universe is very big and there are many of them existing,
Yeah.
and we need to do statistics with many objects. If we do
Okay.
this statistic with a bunch of, let's say, 1,000 galaxies, 100, we will have some bias. We will have
Okay.
some results that can be problematic. So
Okay.
we need, since we can access to it, as much as information as we can.
So more galaxies mean you are getting the more precise data.
Yeah, that's it. When you do a mean calculation, if you have only 5 points, if you want to measure, I don't know, the height of a group, if you only measure 10 people heights, you can get noisy results, you can get bias. But
Yeah.
if you do it with a million of people, you can get a better estimate.
Okay.
It's
So
similar.
in when you were talking about the DESI and Euclid, you
Mhm.
said there are some future missions that are planned
Yes.
which allow us to observe the farther part of the universe or the very close part of the universe.
Yes.
So how do you decide, like how do we know how far a galaxy is from us?
Yes, this is related also with another fundamental aspect, which is that light has a frequency.
Okay.
So when we observe light, it has some frequency that we can explore, and that's why we see some light green, some light blue, because it has a different frequency. What happens is that when a source that emits light is moving with respect to us, this light gets a little bit distorted.
Stretching like a rubber seat.
That's it. That's it. And also, if it comes close to us, it can get more short instead of stretch, become
So
shrink. No.
people who's listening to us can think it like you are standing on a road
Mhm.
and an ambulance is just passing by you. So as the ambulance approaching towards you, you are seeing the increase in the volume of that sound, like
Mhm.
it's ambulance sound. It's
Yes.
increased, and as it passed you, you'll see the intensity of the sound that you're receiving from the ambulance is going to decrease.
Yeah, it's a
So
good
this
example.
way you can think like
Yeah.
the light also behave in the similar manner when we are thinking about wavelength or the frequency.
Mhm. And for example, I think it's another good example. We can study a star like the sun. We can see how the light of this star is perceived by us, and we can see that this light, how much it was stretched.
Okay.
And by measuring how much it was stretched, we can have an estimate on the velocity of that object with respect to us. So
Okay.
with studying another light property, this stretching of the light, we can see how far away and how fast is that object moving.
Moving.
Yes.
That's really good. Like
Yes, it's amazing.
we talk about many times the galaxy distribution. So
Mhm.
what they are telling us.
Well, the main point in the galaxy distribution is that at the smaller scales, I mean, scales of quite close to us in our the Milky Way and our cluster of galaxies close to
So
us.
when you say close,
Yes.
so can you give us rough estimate, like so people can relate? When we say close, how far something is. When
Yeah.
we say far, so how far it is.
Yeah. Let's say some light years scale.
Okay, people
Or
don't know the
the light
scale
year
either.
scale is just, let's say, I don't know is the exact factor, 2 kilometers, but I think it's in the range of it's around billions of kilometers.
Okay, so we can think in that way. The light takes 1 year to reach there, basically.
Yeah, if we can define this light
Like,
year, then
so the more the time light is taking to reach there,
Mhm.
the further the object away.
Yes, that's it. And more than into get into the distances, my point is that if we just focus on a small patch in the universe, we can see that we can have galaxy there, a galaxy cluster there, maybe some objects as a black hole or whatever over there. But if we zoom out and we have the structure of the whole universe, it's more distributed like in big filaments, and we can have some voids and filaments, but in general it quite looks homogeneous. Yeah, and I mean by that
Looks
it
similar at large scales.
yeah, it doesn't matter if you zoom in one part or another, you
Yeah.
see like the same thing. If you zoom in, of course not, because if
Yeah.
you zoom enough, you can even found Earth, which is quite a strange object in comparison to the rest of the universe.
Yeah.
But if we can take this zoom out, we will see that really the universe looks similar in different regions. You go to one extreme and the other of the universe, and wow, they look like exactly the same. How is that?
Yeah. Okay. And we use two technical terms again here, like the void
Yes.
and other word I forgot, like what you use. So can you explain what void means here?
Yes, I guess the other is homogeneity, I guess. But homogeneity, I think, is the thing that I explained, that
Yeah.
the universe is just at certain scale, it looks the same.
You use
Void. Yeah, void is just as we can have
It's just the
cluster.
empty space, I guess.
Yes, we can have cluster of matter, but also in the part where there is no matter, there can form also places without matter, big places without any matter, very few matter inside.
Okay.
And these are called voids, which are at the end are other structures that are formed in the universe, but they can be defined as the absence of matter
Okay, so
inside.
when we say there's less matter in void,
Mhm.
so what observation have you made? Like you have observed that particular portion of the void using optical light or infrared, because things get changed when you just changing your optical filters, I would say.
Yes. Yeah, it depends in the frequencies that you see with different filters. Different filters leads you to observe X-rays or even redder light or more blue light, and with them you can get like a complementary way to study different objects, because some galaxies emit more in the X-ray range,
Yeah.
and if you saw them with a radio or with your eyes, you cannot perceive anything. But if you put an X-ray filter and you study just light emitted in that range, you can really see, well, wow, there is a big galaxy in here. So it's important to have this complementary approach, to have different filters to study different ranges.
So basically, we can't say the void is completely empty. There's still something there,
Mhm.
but very less compared to the other patches of the sky or the universe there.
Yes, that's it. Good example is just a galaxy that is thrown out of a cluster. It can happen in the normal evolution. Some galaxy can be like kick out of the galaxy, and it can really go to the with the drift
Okay.
and become isolated.
Okay, now we move on to this huge data thing, because as we talk about, there's a lot of data, and there are also the future missions that are planned now. So
Mhm.
we'll be having the huge data access. So how do you think like the researchers separate real signal
Mhm.
from the noise within the data? Like it's a tricky task, because you can see sometimes your noise can perfectly mimic the signal that you are expecting.
Mhm.
So in that sense, it's a really tricky task. So how you manage these things? So my question was, how do you separate real signal from noise? Like people want to know, like when it comes to the huge data.
Yes. Well, I'm not an expert in this, and for sure, so many people are working on this, and they know how to distinguish. But really,
You are getting the clean data. That means
yes. Well, no, I get the data with some noise.
okay.
The data that I work with, this distribution of galaxies, also it has some error, because naturally we study things that can be, the precision that we have is limited, and we can see that, okay, maybe this galaxy is moving with this velocity, but instead of one precise velocity we have a range of velocities, and we study the data with this, with deviations. It can be with better quality, with more precise measurements, but it can be also with worse ones. And yeah, really, the data that we use in general in cosmology, it had the uncertainty of the proper measure. So
Okay.
really, yeah, we have, even in this field of taking data, they know exactly which precision they have and with which error of the data they are dealing with.
So how do you know whether the pattern you are observing after using the data, it's real or it's from your just noise?
Well, for sure, you always can have some contribution of noise,
Yeah.
but it's what we try is to be the smallest as possible. Well, this is really close related to telescopes detecting false signals,
Mm-hmm.
and really it depends really on the capacities of the telescope and the capabilities. So
Okay.
yeah, in my case, I have like to rely in their knowledge, but yeah, I think they have been done this for many years, and they have different techniques to explore and to detect false detections or more noisier detections. So they really have techniques to study the light that they collect and be able to really clean this image and eliminate also contributions I can have for, I don't know, a satellite orbiting Earth or certain event that can perturb the telescope. So yeah, they have many ways to explore this. For example, the detector of gravitational waves,
Yeah.
it was so sensitive
Yeah.
to tiny variations.
Yeah.
So really, they have to account into, for example, I don't know, just a truck passing nearby.
Yeah.
They can measure so it's a little bit similar with a
Okay.
telescope.
We talked about so much data things. So
Mhm.
when we are talking about data, then how can we restrict ourselves
Mhm.
away from probability?
Restrict from probability.
Yeah.
Well, what happens is that, well, in my case, that's an interesting question. If I get it right, if in my case, one trick that we do in cosmology is that we only have, well, the universe, by definition, we only have one, but this property that I told before, what's called homogeneity, that you can have the similar thing in different parts of the universe, a similar structure, what we can do is to study many of them, and they are like mini realizations of a universe.
Okay.
We are getting like different universes studying different patches, but this trick allows us to have more statistical power. But really, statistics is, at least in my field research on cosmology, is a central part of my research. What
Okay.
we do, instead of we cannot see another universe, we cannot have another window to see another universe, what we do is to work with different patches.
Great.
And with them we see, okay, this property holds in this other patch. Yes, okay, and we can get sort of statistics out of there.
Where you also talked about the uncertainty in the galaxy surveys. So
Yes.
I'm just wondering, why is uncertainty not a weakness here,
Mhm,
but actually be an honest part of your process?
mhm. By the process of scientific research,
Yeah.
even, yes, it's fundamental. I mean, in my thesis, which is over there,
Yeah.
I have a quote by the scientist called Richard Feynman.
Okay.
I wanted to look it up because,
Yeah, you can take a look.
yeah, it should be around here. Oops, because I don't like to say the quote
Wrongly.
distorted. Yes, it exactly claims that I like this quote. I think it's over here. Yeah, that's it. What is not surrounded by uncertainty cannot be the truth.
Okay.
And that's I think the more that you know,
Okay.
more than science even, that really uncertainty is a fundamental part of life,
Okay.
and by extension is a fundamental part of the universe.
So here I would like to give a simple analogy. Like
Mhm.
in India, mostly people follow cricket. So I will take
Uh-huh.
the analogy from cricket.
Yes.
So it's like a cricket where one good shot does not tell us about whether a particular player is in form or out of form.
Mhm.
So how do you know if the player is performing well or not? So what you're gonna do? You take the many matches and you just found his average, his strike rate, and then you decide like
That's
whether
it.
it's a good player or not. So that's the similar thing you are doing with lots of data,
That's
different
it.
patches, different maps of the universe,
That's
and
it.
decide.
I said also another good example. The Earth is quite a relic. It's a strange part of the universe. And if you just take the Earth, as you can see that the universe is filled of planets with life of water, and come on, it's just a statistical. It's just a particular element. But really, we have to have the big picture to study there. As you said, to study the whole with time, to study how this player plays and the statistics of this player.
Okay, thanks. We'll stop here. So we'll
Okay.
continue tomorrow.
Perfect.
Thanks for your time.
Perfect.
हेलो दोस्तों, ये एपिसोड अभी ख़त्म नहीं हुआ है। हुआ ऐसा था कुछ कि जब हमने ये रिकॉर्डिंग करना स्टार्ट किया था पॉडकास्ट, तो हमने नहीं सोचा था कि हम इतना कन्वर्सेशन करेंगे इसमें। लेकिन रिकॉर्डिंग के दौरान कन्वर्सेशन इतना इंटरेस्टिंग बना कि हमने काफ़ी सारे टॉपिक्स कवर किए हैं। और रिकॉर्डिंग के टाइम पर चीज़ सामने आई कि जो हमारे गेस्ट थे, उन्हें अपने किसी पर्सनल काम के लिए जाना पड़ा। है ये कि मैं इसको क्यों पार्ट्स में बना रहा हूँ। और दूसरा रीज़न ये है कि हमने इतनी सारी बातें करी हैं इस कन्वर्सेशन में कि वीडियो काफ़ी बड़ा बन रहा था। तो मैंने डिसाइड किया कि इस एपिसोड को 2 पार्ट्स में मैं रिलीज़ करूँगा। तो आप बने रहिए पार्ट 2 के लिए हमारे साथ में। और अगर आप लोगों को ये वीडियो पसंद आया, आप लोगों को इससे कुछ जानने को मिला, कुछ अच्छा सीखने को मिला, तो प्लीज़ सब्सक्राइब कीजिए साइंटिफिक पंचायत को। तो बने रहिए मेरे साथ। मैं मिलता हूँ आप लोगों से सेकंड पार्ट के अंदर। तब तक के लिए बाय।